So in this segment, we're going to start a different unit in which we will start by talking about balance of energy. Okay, in particular the balance of mechanical energy, and then we'll go on to looking at alternate measures of stress, as they are called. Okay, so in this unit we are going to look at the balance of energy. Now we're going to look, at least for now, at the balance of mechanical energy only, because if we want to talk about other forms of energy, such as heat, energy related to heat and so on, we have to energy related to heat, and maybe also the energy associated with transporting substances. We need to define a whole lot of other quantities which we haven't yet done. So we'll focus on mechanical energy, and at another time we will sort of enhance it by including other types. Okay, so all right, we're going to talk about the balance of mechanical energy. The next thing we're going to do is sort of go back to the idea of stresses, but also look at additional measures of stress. Okay, what we will see is that there are other stress tensors we can define besides the Cauchy stress. And then we're going to sort of return to this idea of energy, and in that context look at the notion of what we will call work conjugate relations. Okay, we'll see what we mean when we get to it, of course. And then, right, and that will then lead us on to the next unit. Okay, all right, so this is the plan for this unit. So let's start then with the balance of mechanical energy, right? All right. Here's how we're going to look at it. So let's start out by saying that we have the body in its current configuration, right? And we have some forces acting on it, right? We know that for any point here x, there is a body force. Let's denote that as BF, right? This is a field. And then we also know that if we have some subset of the boundary which we denote as the traction boundary, right, with its unit outward normal, we know that we have a traction vector field on it. All right, this is the setting we have. Now, in this setting, we can ask ourselves, what is the rate of work, or what is the power expenditure of these external forces? Okay, so we can ask ourselves, what is the power expended by external forces? Right, or just what is the power of the external forces? All right, let's define that as P external for obvious reasons, right? And this, if we think about it, is simply, we're talking of power, right? So it is each of those forces multiplied by the corresponding velocity, right? Okay, so we have here integral over omega t Bf dotted with v, the spatial velocity, integrated over the volume, plus the boundary traction T dotted with V dA. All right. Okay. So now let's go ahead and write out what we get from here by simply applying once again our Gauss divergence theorem. Okay. So what we do first is, of course, recall that T equals sigma n, right? And this is the Cauchy theorem. Okay. Now, for certain technical reasons, what I'm going to do here is say that actually the boundary of the body that we were considering, the traction boundary, is the full boundary, right? This is purely for technical reasons, because if I don't do this, I need to define a whole lot of other things which may sort of take us away from what we're trying to do here. Okay, it'll take us away from the main thrust of this idiom. So let's suppose that we have this condition. All right. So what this lets us do, if we have this, and then we also combine it with the fact that the traction is related to the stress in that manner, what we have is that the external power is this, the body force dotted with the velocity plus now integral over the entire surface sigma n dotted with V dV. Okay? All right. Now, the situation that we want to get to is we want to convert that surface integral, which is the second integral here, also into a volume integral, and we do this using the divergence theorem. Okay? So the way we can write that is to first realize that this we can rewrite as integral over partial omega t. We can write this now as V dotted with sigma, okay, which gives us a vector, right? The resulting vector dotted with n dA. And I realize I made this a dV, it should be a dA here. Okay. Now on this form of the surface integral, we can apply the divergence theorem. Okay. So the first integral stays the same. Okay. On the second integral, now we know how to do this, right? We just look at that as divergence of the vector v dot sigma. Okay? So we get here integral over omega t, right? By the divergence theorem, we get divergence of v dot sigma dV. Okay? And this is from the Gauss divergence theorem. All right? Okay. Maybe it's useful to rewrite this term in coordinate notation. It is integral over omega sub t v I sigma ij, okay, giving us free index j, the whole thing, comma j. All right, that's what we're doing here. And when written in that form, in particular, you can see that we can essentially now apply the product rule of differentiation here. When we do that, what we will see is that the j, the derivative with respect to xj, is going to be applied to vi first and then to sigma ij. All right? So, what this gives us then is that the external power is integral over omega t Bf dotted with V. I'm going to include the other terms here. Okay. The first term that we get is of the form spatial gradient of V contracted with sigma, and the second term is V dotted with the divergence of sigma. Okay. All of this dV. This term in coordinate notation again is just Vi comma j, that is the spatial gradient of V, sigma ij, and observe that in this product both indices I and j are being contracted out. And if you think back to the way we defined the contraction of two second order tensors to give us a scalar, you'll see that this is exactly that operation. Okay, and hence we write it above as spatial gradient of V contracted with sigma. The second term then is Vi sigma ij comma j. Okay, right, and that we see clearly to be V dotted with the divergence of sigma. All right. So now if we look at this, we observe that we have two terms here that actually are very similar to the balance of linear momentum. In particular, if we look at this term here, we see the body force dotted with V, and here we see the divergence of sigma dotted with V. You'd recall that the only term missing there then is the term V dotted with the material time derivative of the velocity itself, right, times the density. So in order to make that clear, let's write this all out in the following form. So I'm going to write this as Bf plus divergence of sigma minus rho. Now just for the sake of brevity, I'm going to use this notation that we've little used in this class, but I'm going to use in this series of lectures, I'm going to use that notation for the material time derivative of the velocity. Okay, because otherwise I need to add the specification that this is with respect to holding the reference position fixed and so on. Okay, so that's the material time derivative here. Okay. All right, we have this, but then we added that term in, right? So what we have to do back here is we can include this term, which we must, but then we have to subtract, back here all of this is dotted with V, okay? And here we have to, since we subtracted rho dV dt here, we have to add back rho dV dt dotted with V. Okay, all of this integrated over the volume. Okay, and what we've done here is just add and subtracted rho dV dt in order to see that this entire term, this entire contribution, combination of terms is what? This is basically the left-hand side of the balance of linear momentum, right? So when these terms appear together, they're equal to 0 because of balance of linear momentum. All right? Okay, so what we see finally is that the external power is equal to integral over omega t grad V, the spatial gradient of V contracted with sigma plus rho material time derivative of the velocity dotted with V. okay, dV. Now, the spatial velocity gradient, is it symmetric? Think about it. In general, it isn't, right? In fact, when we first introduced the spatial velocity gradient, we wrote it out in terms of its symmetric and skew-symmetric parts, d and omega respectively. All right? So d is the rate of deformation tensor, which is symmetric, and omega is the spin tensor, which is skew-symmetric. All right? But sigma, however, is symmetric. Right? And then when this type of a contraction appears, something we discussed when we were talking about tensors, about basic tensor properties, is that in this sort of a contraction, the skew-symmetric part disappears because sigma is symmetric, right? So this contraction picks only the symmetric part of the spatial gradient of V. All right? So as a result, what we see here is that the first term is sigma contracted with the rate of deformation tensor. Okay, I should also say here that this term is symmetric and this term is skew. Okay, what about the second term? We see that we can actually write out the second term as 1/2 rho ddt of V square, right? Right? But when that happens, you observe that this term is what? What is that term? We have rho ddt of V the whole square, right? Or the magnitude of V. What you should be able to see in there is the kinetic energy lurking. Okay? The reason that works out is the following. We have now integral over omega t, sigma contracted with d, okay? That's the first term, plus, I'm just separating out these two integrals here, and then I'm going to do something which will make clear that this term really is the rate of change of kinetic energy. This is what we have, right? Now, what does the Reynolds transport theorem tell us? The Reynolds transport theorem tells us that this is really just d dt of integral over omega t 1/2 rho V square dV, right? This is because of Reynolds. Okay? But then this quantity is what? We recognize rho dV as being an elemental mass, and the magnitude of its velocity square multiplied by dm gives us essentially the and 1/2 of that gives us the kinetic energy, right, of each elemental mass. Integrated over the volume, it gives us the total kinetic energy. Okay? This term here is an interesting one. What it is doing is to give us the stress acting on a rate of deformation, right? This is the so-called stress power. What this term does is that we have our body in its current configuration, and there's a certain stress, right? There's a stress distributed throughout it. The stress doesn't have to be uniform. It could be varying. Now, each at every little neighborhood of the body is undergoing some rate of deformation, right? So as I'm squeezing it, I'm trying to show you that that different parts of the body are deforming at certain rates, right? Because of this deformation that I'm imposing by squeezing it, you can calculate a rate of deformation tensor d, as shown there, right? This thing's happening at a certain rate. There's also a stress generated there. What that first integral gives us is the work done by the stress on the material, right, as the stress deforms that material. Okay? So this is literally the effect of, this is just like a force acting on a velocity, except now written in terms of stress and strain, or stress and rate of deformation, which are the relevant quantities for continuum bodies, right? So this term then is called the stress power. Okay? All right? Sometimes people will also refer to the stress power as the internal, well, they sometimes use the internal stress power. Okay? And for this reason, it's also sometimes written as P internal. All right? So what we have then as our final form of the balance of mechanical energy is the following. The work done by the external forces on the body, because that's what we started with, actually the power, right, of the external forces on the body, because we were looking at a rate term. The power of the external forces on the body goes into the stress power, which is that first integral, which tells us how the stress is acting on the material surrounding it and deforming it and thereby doing work on the material. All right? And it also goes into changing the kinetic energy of the body. Okay? And if you think about it, this is essentially a very much reduced version of the first law of thermodynamics. Okay? On the left-hand side in this case we have work, and on the right-hand side we have the change in internal energy of the body, okay, for an elastic body. Okay? So this would be change in internal energy for an elastic body. I recognize, of course, that we have not yet provided a rigorous definition of what we mean by an elastic body. Okay, but for now, just assume that that's the only thing we ever know.